All right, so let's get into it. Today I'm going to talk about transformations. You've already seen some of this stuff, to be honest. You know, I've come across scaling and translating and rotating things already, which this doesn't include rotating, but we'll talk about those as well. And I'm going to combine this with some code examples as well. So I'm going to be switching between Visual Studio and the lecture. So let's kind of dive in. You probably already kind of have a pretty good intuition at this point about vectors and how to apply matrices to vectors. So in short, right, we can represent the vector x and y in the matrix form of x and y in a column format. Which is a 1 by 2 matrix, right? And now we can apply matrix transformations to it. So if we took a 2D vector, we wanted to apply an identity matrix to it, we would have a 2 by 2 matrix. If we wanted to do that with a 3D matrix, we'd have a 3 by 3 matrix, right? So adding vectors in a matrix form works exactly the same. In fact, everything is pretty much the same as before. When you add two matrices together that are vectors, like two vector matrix form vectors, you're just taking a point and you're applying a vector to it and you're moving it. And that's, I think, at the core of some of these transformations. For translation, right, you have a point origin of your object and then you move it by some amount. And so let's kind of look at that really quickly. So let's open up our code. And I'm going to be using the example of the mesh class that we've been developing recently. So let's make a little quad, and the quad is going to be equal to we're going to make a small little quad that's going to show up on screen. Great. Let's turn off that rotation that we have, so that it's no longer doing that. And so right now what we have is going to be just a bland little quad that's sitting there. Oops. Great. Awesome. It's still a little bit too big for my taste. Let's make it even smaller. I'm not sure why it's not getting bigger or smaller. Well, let's not deal with that now. Right now, the size of the quad is being set here, so let's just make it smaller here manually. Cool. Now I have a little quad. And like as we talked about in creating this, we could manipulate these vertice values, right? But instead, we're going to leverage the the vertex shader to multiply our model matrix. And if we take a really quick look here, we can see that the model matrix is just an identity. So let's use one of the GLM matrices. We're just going to use the translate matrix. We're not going to talk about what the translate matrix looks like quite yet. We're going to talk about that in this lecture. But let's do a, well, we see it literally right here. So let's copy that. So we're going to start off with the identity matrix here, which we're going to translate by some vector, which we're going to set up here. Vector point origin, which is going to be equal to a GLM vector 3, 0, 0, 0. That's the reason why I'm doing it this way. Great. So now when we render it, when we run it, it should look the same. It should be at 0. Now, going back to this, we have now a point origin, and we want to apply to it a vector, and we want to move it from one place to the next. And so the way we would do that is really point origin plus equals a GLM vector 3. And let's say we want to move it by 1 unit on the x-axis, right? And keep in mind, this is then being used by this translate transformation, so ignore that. That's how it works, but we're just looking at how moving a point that's at 0 by a vector by 1 is going to move it. Now we've moved it by 1. We can do that by any arbitrary number. We can go 0.3, and we can even do it in z. We have a projection matrix, so it should get smaller if we move it farther away from us. Right? Great. So you can kind of see that when you take two vectors, and one vector acting as the position, and when you add to it another vector that represents a translation, it'll go from one place to the next. And so we can actually take all of these different transformations, and we can kind of squish them down into a linear combination of matrices and of transformations to get to one matrix that represents all of the different transforms and all the different things that we've done. And actually you can see that already in this code. When you look down here, right, you can see that we're passing in one matrix, and that matrix is the model matrix times the view matrix times the projection. All of that gives us the information to then know how to manipulate an arbitrary point in space and get it to be on the screen in the way that we want it to be. And that's a pretty eloquent kind of realization. So you can't just add matrices in the same way, like you can't just multiply matrices in the same way that you can do with numbers. If you take one matrix and multiply it by another matrix, they have to match in a certain way, and that way is explicitly the number of columns on the left matrix has to match the number of rows on the right matrix, and that's because of the way that matrices are multiplied. In short, the way matrices are multiplied is you take each row and take the dot product of the equivalent column of the next matrix that you're multiplied by on the right. And you kind of do this sort of thing with the appropriate location. And that's how you get, so for example, if you take a 3 by 3 matrix, like here, multiplied by a 3 by 1 matrix, the number of columns matches the number of rows, and the output is actually a 3 by 1 matrix. So those two inner numbers, the 3 by 3 and the 3 by 1, the 3's go away and you have the 3 by 1. If you need a refresher on matrix multiplication, I recommend you check it out on YouTube, the Khan Academy. Videos are quite good. And you still have that same outcome. So what's really cool, let's talk a little bit about what happens when we mess with the matrix a little bit. So let's go into our code. We've already done this actually at one point where we were messing around with the diagonal. So let's play a little bit with this model matrix here. Let's go down here. And what happens if we mess with the diagonal? So right now we've set up the model matrix as just being the identity of 1, and that's 1. What happens if we change it to 2? Nothing. Oops. Well, that's because of a particular aspect of this thing. So let's not do it like that. Let's change it so that we have now M4 model 0, 0 is equal to 2.0. Let's do that for the diagonal. So we've left the last 1 as a 1, and I'll talk about why that undid this. Now it's bigger. It might not be obvious, so let's make it super big. I'll take up the whole screen. Right. Great. Versus 1, and we've got 1. So the reason is, if you think about it that way, that dot product of each row by each column, you can see that the output is actually giving us twice the value of the x, y, and z respectively. And that's a scaling matrix. Really, you know, you can actually do it independently. So if I want to make the y bigger, notice I just multiply, I change that particular value. It'll make it larger in that way. If I want to make only the x bigger, I can do this as well. Now you may be wondering, well, what happens if I do z? Right? Well, we're going to have to rotate it to actually see what's going on. So let's take this code here. Now if I scale this by z, nothing will happen actually, because this particular thing we have has no size. So let's go to a quad, to a cube instead, which I think might be nice to see the differences here. You'll notice that now our object's going to extend out into the z. Right. It's going to be a little bit too big for comfort. Okay, so this is what it looks like normally. Let's make our cube tiny. And when we increase the z by 2, you'll notice that now we have an oblong, but in the long direction. Should be bigger now. Great. Now we make this is how big it is normally. And let's make it bigger in z. Apparently not. Okay. Y works. X will work. Unclear why z is not giving us what we want here, but either way, I will get back to you on that. Another thing that's kind of cool is if you change this value, you're actually going to have an inverse effect. And that's why I was having before. If we set the diagonal, that last value is going to scale everything. So if I make this, for example, 10, it's going to make it really, really tiny. So it's going to divide it by 10. Equivalently, if I want to make it twice as big or 4 times as big, I can just use the inverse of that value. Because what happens is the way that the matrix math kind of fleshes out, that becomes a multiplier on everything. So if you just set the diagonal equivalently to all the values, you're going to get kind of this sort of scalar value based on this. And that's what's nice about that. You don't actually have to change all of these manually. You can just change the 1 in the end, and that will tend to be sufficient. I'm not entirely sure why our z value is not being affected here, but matrix math is confusing and doesn't always work the way you expect. Anyways, I'll figure that out later. It's going to bug me all day. So yeah. So when you take this diagonal and you multiply it, what happens is all these values get multiplied by 2 and everything scales out. Similarly, we talked a little bit about translating to a matrix. And this gets a little bit harder to kind of do because you saw that before the way that we did the translation was manually. We would actually move things and then create a translation matrix around that. So like, how does that work exactly? Well, it's clear that changing the diagonal isn't going to give us this effect, right? Let's go back to a normal thing. It's not really going to work. So if we want to, get a translation, it's clear that we can kind of do both. We need to kind of understand how to combine these kind of linear transformations such that we can get multiple things one after the other. Let's see how we can do that. So let's play around with this. So let's create one model, one matrix. Let's call this the scaling matrix. Let's ignore this rotation stuff for now because we're going to do this manually in a second. Scaling, and then what we want to do is we want to add the scaling matrix to the model. Is that what we want? What happens if we add the scaling matrix to this? And let's take this code here and put that there, and let's make everything twice as big. So what we want is this should be just like before. We have a matrix that scales it by 2 and does nothing else because we just added it to the identity. It's not exactly what we wanted. If we do, for example, if we compare these two, it might actually look the same, but it's actually mathematically should not work. It's actually incorrect mathematically. And the reason is we're taking an identity matrix, and we're adding to it the scaling. You'll notice if I change the scaling here to 3 or something, it won't look exactly the same. It just happens to be that 1 plus 1 is 2, right? So this versus this should not look the same because I guess it does, but either way, the point I'm trying to make is the diagonal is being manipulated. You're adding one uniformly to the diagonal, and that happens to make it look the same. But really, the way we want to do it is we want to multiply, and that's kind of the way that you combine these transformations together. Is you take one and you multiply it by another. And so we would just multiply this. And great. To generalize this a little bit more, you almost want to have 3. You want to have the translation, the rotation, and then the scaling. And generally speaking, the way you combine these is really important, right? You don't want to translate, you don't want to scale something that's been translated, and you also don't want to scale something that's been rotated, although generally speaking, those two are relatively interchangeable. So you have to think about it almost like what gets applied first. If you were to take the vertex, it goes on the right side, right? It would go here. So you want to apply scaling first, and then the rotation, and then the translation. Great. Now, let's talk a little bit about what all these do in a second, but let's just see that this still works. And this should give us just a scaled up thing. Cool. So let's talk about rotations. Let's not talk a little bit. We're not going to derive how these are defined, but you can spend a fair bit of time to kind of do this with a piece of paper and understand how to apply this rotation to a vertex. The values are pretty straightforward, and so let's try to create a Z rotation in our code. So as you can kind of see here, you'll notice that it's largely an identity matrix, except for the top left corner, which is cosine, sine. So let's do cosine of theta, and then negative sine of theta, and that's going to be 0, 1, right? And then 1, 0, and then 1, 1, and that's going to be sine theta, and then cosine theta. And we need our theta now. Cool. And we also need to use the correct matrix here. And this will just do rotation in Z. Let's see what happens. Great. And now notice if we scale, let's add this to, this is kind of a silly way to do it, but it'll scale with the rotation. And theta's in radians, so it should hopefully scale slowly. You can see that the scaling and the rotation are applied independently. What happens if we change these two? Allegedly, nothing should happen, because when you rotate something, then you scale it, you're still about the same. You're still about the same coordinate frame. So cool. You can do this with y, you can do this with z, and you can do this with an arbitrary x, y, z or a quaternion. And the derivations of those are pretty involved, and I recommend you go look them up in when you need to do them. And yeah, this is the x as well. So you can actually combine these in whatever linear combination you'd like, and you're always going to kind of get the same thing on the other side. So let's talk about the 4x4. We've been using 4x4 here the entire time, but you'll notice that translation is not something we were able to really crack the nut on. Like, how do you get an addition? How do you add a vector to this? Well, you can kind of notice that if we take the matrix into a diagonal, and if the last value of our vector, like now we have to take a vector, and the vector has to have 4 values as well. We can't have this 3, we need to have a 4 if we want to multiply it by the matrix. But if the 0 is there, then any time that we multiply it, we'll always get a 0 in that last position. And I think that's really important, even if it's a scaling or whatever. We already saw some of the effects of the W value in terms of scaling. If that last value is 2, it kind of applies a magnitude change to things because of that last when it's not 0. So if we change it to a 4x4, we now have to consider that last W value. And so this is when we start to see how we can do actually a translation. Because if we then leverage, if we put a 1 in the W value, in the 4th value of the vector, then anything in the last column of the translation or the transformation matrix will be preserved. So if you have an x, y, z 0, these values will just get thrown away. That's important, because now you can think of x, y, z 0, where the W value is 0. You can think of that as a vector, because vectors don't get translated. However, a point does get translated, And so if you have a point, you want to have that last value be a 1, because then our last column can then be added to it, because that dot product will simply add that value to 1. And so the way that we do this, you can imagine our translation matrix now. Let's copy this over. This is always going to be the last column. 0, 1, 2, 3, and generally speaking, we set this as a 1, so we're not going to do. And now this is going to be our, say, our point origin above dot x dot y dot z. And notice, let me get rid of this. So let's just test that it all works the same. Cool. And so now let's say we want to translate it by x. And what's cool here is we can actually, instead of applying it directly to the translation matrix, we can just do this, plus equal to 0.01f. We're just going to increase the x by 0.01 every frame. And it should now move. Although it might not move quite fast enough. So let's do this. Let's first turn off the rotation. You'll notice hopefully it's moving ever so slightly. Not moving. Okay, so here we go. We've got an issue here. Why is this not working? And this might actually get pretty involved, because I realize now that's unique. Let's see. There we go. The reason is now we have a perspective projection, don't forget, so it's going to look a little bit different. Right, the reason it's not moving is because we're not actually, it should be this. Sorry, it should be that. It's not being updated every frame. Static means that it's only initialized one time and that memory stays there forever. So now it'll move to the right, a little bit too fast. And you can kind of see this will work. Sorry, it was a static thing. So now it's moving to the right. And the reason is we're adjusting these values, the x and the y and the z, in that last column of the translation transformation, and that's being applied to this vertex. Great. So now you can kind of see how you can do this. For example, start to do wackadoodle things. What we're trying to do is just give it a little bit of random behavior. Just give it a little bit of random behavior and it'll sort of bounce around a little bit. Cool. And we can bring in back that rotation, again, just for kicks. And so you can see how you can kind of combine these together to create pretty interesting behaviors that are actually, you know, can be quite physical at times. And let's have it move to the right a little bit more, so you can kind of see it go this way. And yeah, you can see the projection matrix, and this is an innately physical object, a three-dimensional object, and all of these transformations remain correct in their combinations. So yeah, that's about it. I mean, those are the three main kinds of transformations. You have the rotation, translation, and scaling, and it all breaks down into really just one transformation that then gets passed to the shader, and on top of that, then you apply a view transformation. So it's really just another one of those sets of rotation, scaling, and translation matrices that represent the view of the user, or the view of the camera, right? Because if I don't want to render from the perspective, from the coordinate system of the object, because I'd be inside of the object. I have to then move the object to where it would be respective to me, and then the final transformation is the perspective or the projection matrix that can be perspective or orthographic, and that will map that data down to the flat plane of my screen. And so now you kind of have all of the different transformations that you need to really kind of create pretty much everything that you need for most of the common stuff for game engines. Great.